This video is going to deal with compound interest, particularly continuous compounding. So we want to find the time to reach an investment goal. Now, interest can be compounded annually, once a year, semi-annually, twice a year, quarterly, 4 times a year, monthly, 12 times a year, daily, 365 times a year, and of course, today we're going to focus on continuous compounding. So let's read what we have here. So it says the formula T equals ln of A, so this is the natural log, so it's the base E. ln of A minus ln of B divided by R can be used to find the number of years T required for an investment P to grow to a value A when compounded continuously at an annual rate R. Okay, so the actual formula for this is right here. A is equal to, so A is the future value. Okay, it comes from P. You invest P, and in T years, you get amount A. So A equals to the investment or principal P multiplied by E to the RT. Again, R is the annual rate, T is the time in years. Okay, so now, using this formula right here for part A, how long will it take to increase an initial investment of 1,000? Okay, so you're investing 1,000. You want it to grow to 8,000, and the rate is going to be 10%. Okay, how long will that take in years? So basically, you just plug in your values here. You could actually put them into this formula if you wanted to, right there. Okay, and use some logarithms, base E in particular, and you can find T. But since they give you the formula here, we're just going to plug it in. So I take the calculator out. So it's ln of 8,000 minus the natural log of 1,000. Hit enter, and then divide that by the interest rate, which is 0.10. So this gives me 20.79. 20.79, rounded out to 2 places. And that, of course, is in years. So to grow $1,000 to $8,000 at a 10% rate, annual rate, compounded continuously, it'll take, well, almost 21 years, but 20.79 years, rounded out to 2 places. Okay, let's clear this. Now, for the next one, what annual rate is required to increase the value of 2,000, a 2,000 IRA to 30,000 in 35 years? Okay. So in this particular case, we want to find R. Okay, so all we need to do is put the R where the T is. So we could easily do that by multiplying both sides by R. So this will be R over here. And then dividing both sides by T. So this would be T. Okay. So the rate is going to be ln of A minus ln of P divided by 35. Okay. So let's just clear this here. So get the calculator out then. So it's ln of 30,000, that's your A, minus that's your log of 2,000. Okay, so that's the numerator part here. Hit enter. And then we're going to divide that. Remember, we want to find R. So R is over here. And this is now T. So dividing by T. Years, that's 35. So that gives me 0.07 when I convert to about to a percent. So we move the decimal over 2 places. So that would come out here to 7.73, but we run it out to 2 places. So let's put this as 7.74. %. 7.74%. Okay. So that's what rate you'd have to have in order for the 2,000 to grow to 30,000 in 35 years. Okay, so let's clear this. Okay. Now for part C, it wants you to derive this formula. Okay, so again, this right here is your formula for continuous compounding, where P is the amount of the investment or present value if you want, R is the annual rate, and T is the time in years, and A, of course, is going to be your future value. Okay, so how do we get this formula? From this basic formula. Okay. Okay, so I have it derived for you right here. Okay, so you can see it clearly. I have a little trouble writing with this little device here, this pen. Because I've got some damage on my nerve endings in my fingers, so it's kind of difficult to do that. So here's your formula. A equals to P E to the RT. So in order to get from this formula to the final formula here, which is the one we used, I took the natural log of both sides. Again, remember that ln stands for natural log. The base is understood to be E. So if I take the log of both sides, okay, so I get this right here. So I get this right here. Okay, and then this doesn't change. Now there's a property of logs that tells you when you have the log of a product, and this is really understood to be you're taking the log of that product. So when you have the log, in this case natural log of a product, it gives you the sum of the logs. In other words, I take the log of P plus the log of the second term. Okay, log of a product is the sum of the logs. Okay, now because this base right here is understood to be E. Okay, so when you see ln, that's the same thing as log to base E. Now if you just have ln or log with no base, it's always understood to be base 10. If it's log, if it's ln, it's understood to be log to base E. Okay, so then because this is E here and we have base E, the log of this thing becomes the exponent. and I just put it on the left side. So what I did is ln of A, brought this over, becomes minus ln of P. That's going to equal to RT here. So this is just RT. And then I just reverse the sides. So I put the RT on this side, and then ln of A minus ln of P over here, divided both sides by R. And I got the original formula. Okay. So there's other formulas also that you can use when you have just regular compounding. If you want to see more videos involving compound interest, please let me know. Give me a comment at the end of the description. Thanks for watching. That'll be it for this video.